Hi, so in this video we're going to be covering exponential growth versus exponential decay. Just some more applications of our log and exponential functions. So let's just go ahead and get into it. So the first thing I wanted to point out here is just that when we have a variable in our exponent, when we are plugging in a value, so we're going to plug in x equals 3 to all three of these. But when I do that, I just have to make sure that my order of operations is correct. On just a base number to the third power, we know that's just 2 times 2 times 2, so that's just going to be equal to 8. But we have to be really careful when there's a number in front of the parentheses. Our order of operations here tells us that we need to do the exponent before we do the 50, or we need to multiply out 3 times 3 times 3 before we multiply that 50. So this would be 50 times 3 cubed, which is 27. And then I can go ahead and multiply that 50 and 27 together. Just be careful there not to multiply 50 times 3 first before you apply the exponent, because that's going to give you a different answer and one that is not correct. Here we have 20 times 3 raised to the 3 plus 2 power. The 3 plus 2, we can go ahead and add that together first because it's grouped together. So this would be 3 to the 5th, and then I want to raise 3 to the 5th power first before I multiply it by 20. So if I put 3 to the 5th in my calculator, that's 243. So 243 times 20, and that gives me 4,860. So just make sure you don't multiply these first before you apply the exponent. You have to do that exponent on the one that it's on first and then multiply by 20. Okay, exponential growth and decay. This is the basic equation for exponential growth and decay. So we have y, which is going to be the final amount of whatever we have. It's a lot of times we're talking about interest or a population of some type, or like a half-life of something. So the final amount of whatever it is that we're talking about that we have is going to be y. A is going to be the starting amount. So if I have like a population that starts with 50 million, then A would be 50 million. The multiplier is this b, the base that's on our exponent. If it said it doubles every so often, or triples, or it's a half-life, that b is going to be that multiplier. And then x is the time that goes by. Actually, x has two parts. It's the time that passes divided by the time it takes to grow or decay. So when we're looking at these, we're going to actually be breaking x into two parts, and it's going to be the time that passes divided by the time it takes to grow or decay. So let's go ahead and look at some examples, and we're going to decide if they are growth or decay. For exponential growth, when it's growing, that means this term right here that's being raised to the exponent, it means it's going to be greater than 1. And that is because if I multiply the same number, so if my multiplier here is, for example, 2, the exponent is going to tell me how many times to multiply 2 together. The more times I multiply 2 together, the bigger my function is going to get, right? It's going to get bigger and bigger and bigger. It's going to grow. However, on decay, if my multiplier is less than 1, and technically between 0 and 1, it's like a fraction, like 1/2 or 1/3 or 2/7 or something. It's going to start to decay instead of grow. It's going to get smaller. And that's because if I multiply like a 1/2 or 1/3 together multiple times, remember that on a fraction when we multiply them, we multiply the top times the top and the bottom times the bottom. So 1/2 times 1/2 becomes 1/4, and 1/4 is smaller than 1/2, right? And then 1/4 times 1/2 is 1/8, and 1/8 times 1/2 is 1/16. So it's dividing whatever we have up more and more and more and making it smaller and smaller and smaller. So that's why if I have a fraction there, or a decimal, it's going to get smaller and smaller. So the graphs that we looked at last unit of exponential growth and decay, if it's growth, it's going to start out kind of hugging the asymptote here at 0, and then it's going to quickly grow and increase as it goes to the right. If it's decay, it's going to start out bigger and it's going to get smaller and smaller and smaller. It's going to get closer and closer to 0 the more times we divide it, right? The more times we multiply it by another fraction, it's going to get closer and closer to 0. It won't actually reach 0 or cross 0 because, again, if I keep multiplying 1/2 together forever, it's going to get really, really close to 0. It's like taking a pie and dividing it by 10,000 pieces. You're not getting much pie, but it's never technically going to be 0. Okay. So we're just going to look at some functions and we're going to decide would this be exponential or growth or decay. So again, we're looking at this number right here because that's our multiplier. And so because that number right there is bigger than 1, this is going to be exponential growth. On this one, our multiplier is a decimal. It's below 1. And because of that, when I multiply it together over and over again, it's going to decay. It's going to get smaller and smaller. Same thing with this one. This part right here is less than 1, so that's going to be decay. And then this one right here, because 1.5 is bigger than 1, so it's a decimal, but it's a decimal bigger than 1, so that one will also be exponential growth. Okay. Now there's a lot going on in the slide, but we'll just talk about one piece at a time here. So if I want to find my multiplier, again, that's b. That's this number right here, the one that gets raised to the exponent. If my story problem or whatever says that I have exponential growth, that means I'm going to take the percent that it grows and I'm going to add it to 1. I'm actually going to change it to a decimal first and then add it to 1. So if a population doubles, that just means it's going to be 1 plus 1, right? So it would be 2. So b would equal 2 if it says that something doubles. Because you would just take whatever it was and times it by 2, right? If it triples, it's going to be 3. But here, if it says it increases by 20%, 20% in decimal form is 0.02, and that's what I'm actually going to add 1 to. So 1 plus 0.02 is just 1.02. Whoops, not 0.02. 0.2, because I would move my decimal over twice to undo the percentage. So the growth multiplier would be 1.2. Okay, if it's 75%, I would change that to 0.75 and then add 1 plus 0.75, which will give me 1.75. So that would be my multiplier. Now, if I were just to multiply it by 0.75, that would actually make a number smaller, right? If I take 12 and I multiply it by 0.75, that's going to be 8 out of 12, or 9 out of 12, which one? 9 out of 12. So it's going to actually make it smaller. So that's why I have to have the 1 in front of it, is because that's going to multiply whatever it is by 1 so that we keep that whole part. But then it's going to increase it by that 75%. Decay is the opposite. I would want to take the percentage in decimal form, and I would want to subtract it from 1, and that would give me the amount to multiply by to have it decrease by that much. So for a half-life, it would just be 1/2, because 1 minus 1/2 is still 1/2. So my multiplier would be 1/2 or 0.5. If it decreased by 20%, that would be 1 minus 0.2, and that's 0.8. Okay, so that makes sense. If I take a whole and I multiply it by 0.8, I'm going to get 80% of whatever was there, and that means it decreased by 20%. For 0.75, it would be 1 minus 0.75, so it would be 0.25. That would be the multiplier. Okay. To find the time, this is what I was talking about before. So the time is actually, and it's down here, it's actually equal to the time that passes divided by the period it takes to multiply or decay. So on this on these questions, the only thing we want to know is what does x actually equal, and that's the x right here. X is going to be equal to the time it takes to pass divided by the period it takes to multiply or decay. So if it says it doubles every 15 hours, that means the population after 15 hours is always double what it was before. And then it says how much would there be after 30 hours. So this is the time that passed by. So this would be 30 over 15, or 2. So x would equal 2 in this case. If it triples every 0.25 hours, how much would there be after 1.25 hours? Again, the 1.25 is how much time went by, and the 0.25 is the time it takes it to triple, so I would divide it by that, and so that would be equal to 5. It doubles every 4 hours. How much would there be after 30 hours? So again, 30 hours goes by, but every 4 hours it doubles, so x would be 30 over 4. And you could just leave it as a fraction. You could reduce it to 15 halves, or you could change it to a decimal. Any of those would work. Okay. All right, so let's look at some examples. So a colony of bacteria grows exponentially. Initially, there were 300 bacteria. So remember my little equation here, y equals a times b to the x. In this example, the initial bacteria would be a. Remember that a is the initial amount. So a is equal to 300 bacteria. The growth rate is 20% per hour. So every hour, it grows by 20%. The population of this bacteria colony grows by 20%. So that means that my multiplier b is going to equal 1.2. Remember, change it to decimal form, so 0.20, and then add it to 1, so 1.2. How many bacteria will the colony have after 12 hours? So I'm looking for y. I'm looking for the final amount of bacteria. So y equals 300 times our multiplier, which is 1.2, raised to the power of, and we have 12 hours have gone by, and every 1 hour it increases by 20%. So 12 over 1 would be x, which is the same as just 12, right? So in your calculator, try it. 300 times 1.2 to the 12th power means there would be, I'm just going to grab mine really quickly, but check it in yours too to make sure you're entering it correctly. And that should equal 2,674.83. And we're talking about bacteria, so let's just round it. So 2,675 bacteria would be in the colony after 12 hours. Okay, part B is asking us how many would be there in 1 day. So remember, 1 day has 24 hours, and because this is per hour here, we need to change it to hours. So I would just do 300 times 1.2 to the 24 over 1, because it takes 1 hour for it to increase. And so 300 times 1.2 raised to the 24th power is equal to 23,849 bacteria. I'm just rounding it off. Okay. I don't know why it keeps doing that weird line thing. Okay, so here's another example. So the decay, so this one is going to be a decay problem, right? Of radioactive materials. A sodium isotope Na24 has a half-life of 15 hours. So because it says it has a half-life, I know that my multiplier, remember the b here that's being raised to the power, that is going to be 1/2. So this equals b, it's equal to 1/2. It takes 15 hours for it to decrease by half. So that's going to be part of our x, right? So remember, x is time that passes, which it looks like is going to be in part A, 45 hours, divided by the time it takes to decay or grow. So x is going to be 45 over 15 here. Determine the amount of sodium that remains from a 4-gram sample. So this would be our initial amount. So let's go ahead and calculate part A. Now remember here, this is decaying. It has a half-life, which means it's going away at a rate of half every 15 hours. So we expect our answer here to be smaller than the original, right? So if our initial amount is 4 grams, so this would be y equals 4. And then our b, our multiplier is 1/2, so you can put 1/2, 4.5, either one will work. And then 45 divided by 15 is equal to 3. So this would be raised to the 3rd power. And then just go ahead and try that in your calculator. Remember, you want to raise 1/2 to the 3rd power before you multiply by 4. And that's going to equal to 0.5 grams. Okay. So you could try it for 100 hours. The only difference there would be that I would put 100 over 15 as x here, as the exponent. On this one it says 5 days, and so in that case I would want to change that to hours. So multiply 5 times 24 to get 120. So it's 120 hours. So I would, for part C, I would do 4 times 1/2 to the 120 over 15 power, which comes out to, I'm going to try it. Let's see, in the times. So that would be 0.016 grams. Okay, so it's disappearing. After 5 days, there's not much left. Okay, so I recommend that you pause the video and give this one a try, and then come back and see how you did. There are 225 bacteria initially, so this would be our A. They double every hour, so B is going to be equal to 2 because it's doubling the multiplier. Every hour means that every hour that goes by, it doubles, so our X is going to be 6 over 1 because we have 6 hours has gone by. It takes 1 hour to double, so X equals 6. So Y equals 225 times 2 raised to the power of 6. So if I enter that in my calculator, that gives me 14,400 bacteria. So they grow fast, right? After only 6 hours, they went from 225 to 14,400. This is why you can get food poisoning. Okay, one more example here. It's going to be a decay example. So the radioactive element radon 222. So this 222 is just the name of the radon, so that's not one of our numbers here. It has a half-life, and half-life means that our multiplier is going to be 1/2. Its half-life is 3.8 days, which means after 3.8 days, there's only half left, right? So that, when we do X, that's going to be on the bottom, and then on top goes how much time goes past. Determine an exponential decay equation that represents the mass of radon. So at first it's just asking us to write the equation. So we're just going to write this equation, but we're going to enter the stuff that we know so far. So we'll call this one that we don't know yet T on top of X. And we can put, well, we'll put it like that for now. And then, so our equation would be Y equals, we don't know what A is yet, but we know it's going to have a half-life, so our multiplier is 1/2. And then we know that X is going to be the time that goes by divided by 3.8. So that would be the equation. And then it says how much of a 32-gram sample, so that's our initial amount, right, will be left after 7 days. So there's T. It's going to be 7 days, and then we're going to round to the nearest gram. So if I plug in 32 for A, so 32 times 1/2, and then, let's see, how much time went past? Oh yes, 7 days, so 7 over 3.8. So let's go ahead and enter that in my calculator. 0.5 raised to the power of 7 divided by 3.8, and I'm just going to hit enter there, and then times by 32. That is going to equal 8.925, and I'm going to round it to 8.93 grams. Oh, it says to round to the nearest gram, so actually I'm going to round it up to 9 grams. So it went, in 7 days, it went from 32 grams down to 9 grams. Okay, so go ahead and give some of those a try on the worksheet, and just email me if you have questions. Thank you, and have a great day.